Hi, we are going to evaluate the diode power losses of our buck converter, and the approach will be very similar to that of the MOSFET. So here we have the simulation scheme that we have introduced in previous videos, and now we will focus on this Schottky diode. When we want to evaluate power losses in the diode, we have to take into account the current definition and the voltage definition. According to that notation, when we want to evaluate the power, instantaneous power consumed by the device, we have to include this -1. Okay. Once we know that, we will try to identify the different types of power losses we have in this device. First of all, it's clear that we will have some conduction losses because we know that when the device is on, we have something that is close to a constant voltage drop or a constant voltage source whose value in our case is close to 0.5 volts. So if we have that constant voltage source and we have current flowing in this way, we have some power losses. But then we have more types of power losses, as in the case of the MOSFET. Every time we turn on the diode, we have power consumed in that device. The simplification that we are going to do is that since the turn on of the diode is very fast in comparison to a MOSFET, the power losses consumed in the device during the turn on are negligible. This is an approximation, but you can check in the simulation that this approximation is quite close to the reality. You will see that the power consumed in the diode during that turn on is negligible. Then we have the turn off of the device. And in the turn off, what we have to explain is the reverse recovery process, which is a particular effect of the diode that takes place when we have the turn off. Well, in order to explain that in a very simple way, I will try to use this schematic of the buck converter and these simulation results where we see the current flowing through the diode, and here we have the current flowing through the MOSFET. And what we see here is the turn off of the diode, or in other words, the turn on of the MOSFET. Note that the time interval is very short in comparison to the switching period. The switching period is 10 microseconds. Okay, so we only see the turn off of the diode. Well, so let's try to describe what we see, or let's try to describe the different stages that we see in these waveforms. Well, before the turn off process of the diode starts, the diode was driving current while the MOSFET was blocking voltage, or in other words, the current was flowing through the diode and there is no current flowing through the MOSFET. This is something that we can see here. All the current or all the inductor current is flowing through the diode. We see that the inductor current before the transition was flowing through the diode and the current through the MOSFET is 0. Here, the turn on process of the MOSFET starts because, as you can see, the current through the MOSFET rises. At the same time, the current through the diode falls because the total current must be the same, the inductor current. So we will represent that in the schematic in this way. Part of the current is flowing through the diode, part of the current is flowing through the MOSFET. In principle, the transition should finish here because at this point the current through the diode is 0 and the current through the MOSFET is the final value, the inductor current. So in this instant, the situation is this one. All the inductor current is flowing through the MOSFET. But at this point, we have the reverse recovery of the diode. it is translated into a current flowing in the opposite direction. It means that from this point, the diode will drive current from the cathode to the anode, okay, in the opposite direction. So that's why we see this negative current peak here. And at the same time, we see that peak here in the current through the MOSFET. This is something that we already saw in the previous videos. So this peak and this peak are the same, in opposite direction. What is happening in the circuit? So what is happening in the circuit is that during the reverse recovery time, the current, or there is an extra current that is flowing through the diode in opposite direction. That current comes from the input voltage source and flows through the MOSFET. So essentially, this MOSFET in this interval is driving the inductor current plus an extra current due to the reverse recovery of the diode. Well, after some time, the peak, the negative peak in the current of the diode finishes. So here we have the expected value, 0 amps, and here we have the expected value in the current through the MOSFET, the inductor current. So from this point we have this situation. Again, all the current is flowing through the MOSFET and the transition finishes. Okay, what is the simplification that we are going to do here? The simplification that we are going to do is that although we see this negative peak in the current flowing through the diode, the conclusion is that if you evaluate the power consumed by the diode in this turn-off process, you will see that it's negligible in comparison to other power losses. So we will assume that is 0. We are not going to consider it. You can check it if you want in the simulation. And another conclusion, or another thing that we have to take into account is that, yes, we know that during the turn-off we have the reverse recovery, the impact on the diode power losses is negligible, but it will have a high impact on the MOSFET turn-on. Okay, that's why we see this peak. But this is something that we have already taken into account when we evaluated in the previous video the MOSFET turn-on power losses. Okay, so in summary, what we are going to do with the diode power losses? We are going to evaluate the conduction losses, we are going to consider that turn-on losses are negligible, and we are going to consider that turn-off power losses are also negligible. But we know that we have the reverse recovery, and that reverse recovery has a high impact on the MOSFET turn-on, okay, which is translated into higher power losses on that path. Okay, let's see some simulation results. Here we can see the voltage across the diode, the current flowing through the diode, and the instantaneous power consumed by that diode. As you can see here, we have included the -1 term. So, as I said, I will focus on the conduction part, but let me show you that the approximations that we do are let's say, accurate. In this part, the diode is off. There is no current flowing. As a consequence here, the instantaneous power is negligible, is 0. Okay. Then we have the turn on of the diode. We don't see any remarkable peak. So again, we confirm that the turn on power losses of the diode are negligible. And then we have all the conduction interval of the diode, where we see a positive value in the instantaneous power due to the forward voltage drop. And then we have the turn off. Okay, in this part, it's true that we see a peak in the instantaneous power, but that peak amplitude is not as high as in the case of the MOSFET. If you check here in this axis the values, is around 30 watts. But in the case of the MOSFET, I think that the peak was around 250 or 300 watts. So this peak is negligible in comparison to other power losses. In any case, you can evaluate this in LTspice and see the value that you obtain. Well, in my case, I am going to focus on the conduction state, so I will focus on this part of the waveform. Here you have that instantaneous power evaluated during the on state of the diode, so this part is 1 minus d times the switching period, which is around 7.2 microseconds. As we did with the MOSFET, we evaluate power losses by doing the integral of the instantaneous power. That integral is energy. So we want to obtain, let me put that value here, the energy of the on state of that diode. We can use LTspice as we did in the previous videos, and here, as you can see, we obtain the integral of that waveform. As you can see, the value is around 47 microjoules. So as we explained, we can obtain average power by considering that energy and multiplying the value by the switching frequency. So the final value, the power consumed by the diode due to the conduction, is around 4.7 watts. And if you check the previous video, this value is very high, because in the previous video, in the case of the MOSFET, we obtained power losses of milliwatts. Now we are talking about watts. So this is something that we will have to improve in future designs. But for this video, our target is complete. We have evaluated the power losses on the diode, and in the next video we are going to do the same for other components. So see you